Hey, welcome. So, we usually think of complex numbers as, just another piece of algebra, right? Something with an I floating around in it. But today, we're going to pull back the curtain and see what they really are. A super powerful visual language that connects algebra directly to geometry. Okay, let's just dive right in. I want you to keep this question in the back of your mind as we go through this. What if an equation wasn't just some problem you had to solve, but was actually a set of instructions for drawing a shape? Because believe it or not, that is exactly where we're headed. All right, so we all start our journey with complex numbers in the exact same place. It's it's familiar territory, but it has its limits. Yeah, that standard form, z is equal to x plus I, is fantastic for telling us a number's position on a graph. Go this far left or right, then go this far up or down. But what happens if you want to rotate that point, or stretch it? Suddenly, this form gets, well, it gets really clumsy. We need a better set of tools for the job. So let's meet the other faces of our complex number z. Now, these aren't totally new numbers, they're just different ways of describing the exact same point in space, and each one has its own special talent. So on the left, you've got our old friend, the Cartesian form. It's all about position. And then on the right, we have this new way of thinking, the polar form, which is designed from the ground up to handle rotation and scaling. And you'll often see it written in its much more compact and kind of beautiful exponential form, right there. The key thing here is this. We've got a tool for position, and now we have tools for movement. Now, what's really cool about this is how simple these new parts are. The first one is r, the modulus. And look, just forget the fancy name for a second. It's just the straight line distance from the center of the graph, the origin, out to your point. That's it. It's the number's size, its magnitude. And the second piece of the puzzle is theta, the argument. And again, super simple idea. It's just the angle that line makes with a positive horizontal axis. It's the number's direction. So instead of thinking left/right, up/down, we now get to think in terms of distance and direction. It's a total game changer. So you might be asking, why bother with this new perspective? Well, because it unlocks some incredible power, especially when you're dealing with exponents, all thanks to something called de Moivre's theorem. Let's see it in action. Okay, take a look at this problem, which we pulled from our source material. 1 minus I to the power of 12. Just imagine for a second trying to multiply 1 minus I by itself 12 times. It would be an absolute nightmare, take pages of work, and it'd be so easy to make a tiny mistake. But with our new tools, it becomes almost ridiculously easy. So how do we crack it? First step, we switch from Cartesian to polar form. Our 1 minus I becomes a distance of the square root of 2 at an angle of negative 45 degrees. Now, de Moivre's theorem lets us do something that feels like magic. To raise that whole thing to the power of 12, we just raise the distance to the 12th power, and we multiply the angle by 12. The hard work is basically already done. And boom, here's the result. The square root of 2 to the power of 12 is just 64. And half times negative 45 degrees is negative 540 degrees, which, when you spin around the circle, just lands you right back at 180 degrees. So the final answer? A clean, simple negative 64. So elegant. Now, that calculation power is amazing, but believe it or not, it's only half the story. Now we get to the real payoff. Let's go all the way back to our original question and see how these equations can literally draw pictures. This is where that distance and direction thinking really shines. All right, look at this equation from our source. Z times z bar, that's its complex conjugate, equals 16. What on earth is that? I mean, what does that even mean? In this form, it's super abstract. It doesn't look like anything we'd normally recognize. But here's the thing. It's just a secret code. If you swap out z for x plus iy and z bar for x minus iy, and then you multiply them out, all the imaginary parts just cancel out, and you're left with this. X squared plus y squared equals 16. Now that looks a whole lot more familiar, doesn't it? Because of course it is. It's the classic equation for a circle sitting right at the origin with a radius of 4. That abstract bit of algebra, z bar equals 16, was secretly drawing a perfect circle the whole time. And notice, this equation is all about a constant distance from the origin, which is exactly what the modulus, r, represents. It was hiding in plain sight. And you know what? It's not just circles. Different complex equations, which we call loci, describe all kinds of cool shapes. If you have an equation that's about the sum of distances to two fixed points, it's secretly drawing an ellipse. If it's about all the points that are the same distance from two other points, well, it draws a perfect line right down the middle. One of our sources for this explainer puts it perfectly. It says that students often struggle with this stuff not because the questions are actually that hard, but because they miss the logic behind the steps. That logic, that deep connection between the algebra and the geometry, that's what we've been unpacking today. And it's the key to really getting it. So the next time you see a complex number, don't just see it as a problem to calculate. See it as a point, a vector, a set of instructions. Because every single complex equation is telling a geometric story. The only question is, what shape is it hiding?